Thanks very much, Andy. So here's some information about us. We are Weather Decision Technologies. We're a diverse company, 15 years, actually a little bit more, still owned by the founder, Mike Iltz, as a very diverse company that employs meteorologists, data scientists, engineers. We also have an equally diverse client base, have a significant presence in asset protection, agriculture interests, energy trading, and application users. And we're thrilled to be working with Energy Business Watch going on about a year now. And my colleague Ed Berry and I work out of the Houston office, and our specialty is in subseasonal forecasting. So basically focusing on the time frame of about 2 weeks to about 4 to 6 weeks, beyond which we have really reliable model information. And we're using an approach that Ed pioneered, I think it's fair to say, along with his former research colleague, Dr. Klaus Weichmann. This has a significant theoretical and practical underpinning, which is backed up by multiple refereed publications, of which Ed himself is a co-author. And we've been working together for almost 2 years, and I've been enjoying being able to try to do what I can to enhance this approach and make it even more practical. I want to just briefly differentiate what we do from maybe the mainstream. One of the greatest advances in meteorology undoubtedly has been the numerical weather prediction enterprise. I'll just say NWP for short. I think within about the first week, it usually does quite well if you look at the skill scores, and there's even some usable information often through 2 weeks. But you can't use it in a vacuum. And unfortunately, a lot of forecasters tend to over-rely on it. And what Ed and Klaus developed was a physically based system. The fact is, especially when you get into extended range prediction, the signals that we latch onto to make those predictions are weak. And if you're going to find them, you have to rely on careful diagnosis and observational monitoring. In fact, if you look at the practices of the best forecasters, not only in meteorology, but in just about any endeavor, I think one of the things that sets them apart is the practice of observation and diagnosis. Where have we been is a question you have to be able to answer in order to be able to say where you're going, and that is certainly true in the atmospheric sciences. One of the problems with numerical weather prediction is that, as advanced as these models have become, these models of the atmosphere and the ocean system that we run to make predictions, they still suffer from systematic biases, and they have notable predictability dropouts, and it's during times. And the times at which this is most notable are times of transition, from when the atmospheric circulation, the jet stream, is going from one state to another. For example, when the jet stream is fairly straight and circling the globe, and then it goes from that state to one where it breaks down into a series of high and low pressure systems, we know that those are times where the models will struggle with their prediction. And this physically based system that we're using here can help us to catch when those types of transitions and associated breakdowns in predictability are going to occur. We can catch the weak signals that arise from the noise to try to help make subseasonal forecasts, again, forecasts that go out to several weeks, and sometimes even seasonal forecasts, and that's what this physically based system was made for. Also very good for catching extreme weather events and surprises. Well, we have a signal this year going into summer that we think we can rely on to some extent, and that's El Nino. And to set up the forecast, I think a brief review of what El Nino is in order. The normal climatology of the global tropics is one where we have a large body of very warm water spanning the tropical Indian and Pacific Oceans out to almost the date line. The warmest waters, the waters that support persistent large-scale clusters of thunderstorms, which then drive the global circulation, that typically is confined to areas somewhat west of the dateline. And so that's where you see the tropical rainfall patterns that set up these atmospheric circulations that for example, the top right cartoon shows for a La Nina. All La Nina is just an enhancement of the situation that I just described. And when you have a La Nina, you tend to have an even warmer water temperatures over the areas spanning the eastern Indian Ocean to Indonesia. The overlying tropical rainfall patterns are therefore intensified. One of the effects is to shift jet streams poleward in general, thereby creating hotter and drier conditions in the mid-latitudes. An El Nino, which we think is emerging now, is a departure from that climatological state of affairs, where the warmest waters slosh somewhat to the east and take the thunderstorm masses with them. And this alters the circulation patterns, and one key way that it does so is by strengthening the jet streams and shifting them equatorward, which generally creates cooler and wetter conditions in the mid-latitudes. Complication lately has been that over the last actually about the last couple of decades, the Indian Ocean basin has been warming, as has been the Atlantic. And we think that's tied to a longer-term climate change. And this sort of has the effect, like La Nina, of shifting the jet streams poleward and creating more episodes, more frequent and intense episodes of heat and drought. So we have to reconcile those because we do have a very warm Indian Ocean right now. It's considerably warmer than it was during years past for which we have reliable sea surface temperature data, and for those years that we've had El Ninos in the past. What I've done is I've taken a big batch of those years for the era, for the era for which we have reliable data, and I've composited on that on the right. And that's basically a plot of the upper level mass field. It's the upper level pressure field. It looks like some of the annotations have gotten out of place, but generally the purple and blue areas in the mid-latitudes, spanning the mid-latitudes, are low pressure systems, and the yellow-green area straddling the dateline east of the equator is high pressure systems. So those El Nino years tend to see a high pressure system spanning much of the equatorial tropics above the heat source, and to the poleward side of that you see low pressure. So what does this say regionally about the weather for the United States, which this analysis focuses on? Well, if you look at the bottom graphics, there's a lot of white space. What these really are, this is work from Klaus Wolter at the Environmental Systems Research Lab, and he's one of the world's foremost experts on El Nino Southern Oscillation. And what these maps show is the direction in which the risks are shifted for temperature, that's the lower center, and precipitation, lower right. And what you notice is there are a few spots in the U.S. during June, July, and August for which we have a risk of anomalous warmth or cold. Small area of anomalous warmth favored for the summer season over the southeast and also over the northwestern United States, and relatively small areas of anomalous cold that occur more frequently over the southwest and parts of New England and the lower lakes. It tends to be wetter than normal, at least the risk is skewed in that direction over much of the north central states. So this may be somewhat counter to the conception that the entire country is cold during an El Nino event. So how can we use this information to make a forecast? Well, first, focusing on some of the shorter-term factors to get us through the first half of June, the idea is that we're going to see a continuation of El Nino influences, albeit having to reconcile that with the trend, which, as I mentioned, tends to shift the jet stream north. Another thing that tends to happen is that low pressure systems within that jet stream tend to get deposited in the southwest and west central United States as that jet stream breaks down more frequently. That tends to be something that occurs as well when the jet stream shifts north of climatology. So putting all that together, there's a risk of anomalous cool outcomes over the west central United States and perhaps a slight skew in the warm direction over the southeast. However, part of making these forecasts is to acknowledge the uncertainty inherent in doing so. And we try to identify failure modes and directions that pathways the atmosphere could take that are alternate to our most favored predicted outcome. And in this case, we think that the most likely outcome for an alternate scenario would be if El Nino has even more impacts on a general circulation, to the point where the jet stream is not as frequently breaking down into these troughs that get deposited over the western and central United States. That would tend to shift the cooler anomalies further east and would take the wetness further east with it into the deep south and southeast. For the summer season as a whole, we're favoring the same general idea for the most likely outcome. I mean, it seems quite likely that this El Nino event, even though its ultimate strength is uncertain, is going to have a notable impact on the summer pattern. Again, that does not necessarily mean cold everywhere. We think that given the factors that I've mentioned, it's most likely that if we have a cold outcome in the first part of summer, it'll probably exist across the Rockies and the northern tier, with some tendency to extend across the Great Lakes into the northeast. The alternate scenario is based on the idea that in recent years, when we've attempted to, when an El Nino has attempted to emerge, the warm Indian Ocean and other issues related to that have short-circuited the El Nino, and instead what we tend to see is an enhancement of these mid-latitude ridges, a poleward shifting of the summertime jet stream, and warmer risks, especially as we get into mid and late summer. And that's what we've captured for especially our July alternative forecast. By August, if we're going to have widespread durable cold in summer due to ENSO, it tends to occur in the back part of summer because of seasonal sensitivities to the rainfall patterns in the tropical Pacific, among other reasons. So we're sort of circling August, and give or take a week or two of when we could see the most significant cold risks for the continental United States. We would say back half of summer.